আমি কালকে লাস্ট ক্লাসে এবং আজকেরটা আপলোড করব। Okay, let's get started. Okay, now if you go to your course module, if you go to the canvas, okay, let's see the student view. You should be able to see that I have uploaded another module called lecture module, and this is where we are going to upload all the presentations. ঠিক আছে? Is it clear নাকি না? Yeah? Okay.
Yes, sir.
Now, in any case, let's get started. Okay. Oh, before we go anywhere else, okay, let's look at the course outline that we had. So we discussed the course outline. So আজকে হচ্ছে আমাদের lecture number 2. So let's see what's the agenda for today. This is what we plan to cover today, lecture 2. So in lecture 2, we are going to discuss an introduction to algorithms. So we want to discuss about algorithms, okay? And we would also like to discuss the notion of measuring the performance of algorithm. এই যে আমরা বারবার বলছি, we are stressing the fact that in this course we are going to discuss how to analyze algorithms, okay? But before we go ahead and start analyzing all algorithms, it must be very clear to all of us why this is very important. Algorithm measurement can be important. Why is it important that we understand or we see the performance of the algorithm? There must be a reason it's important. তার জন্যই তো এটা একটা entire course almost a large chunk of it is based on that. Yes? So that's what we're going to do today. We're going to look at what algorithm is. I'm sure all of you know what an algorithm is, but then again, I like to start from the scratch so that we are all on the same page. And then after that, we want to stress today, we want to discuss why do we need to measure the performance of algorithms. So that's basically what we're going to discuss today. Is it clear? Is it clear what we are going to cover today? Yeah?
Yes, clear,
Yes,
sir.
sir.
Okay, fine. So now that we know what's the agenda, I think let's just go and start the PowerPoint presentation, okay? All right. Okay, here we are. So I hope you can see my screen. Can you see my screen?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, fantastic. So let's start. Now, okay, so this course is called Design and Analysis of Algorithms. Okay, so you know all these things. This is your textbook. Let's get started. Okay. Now, before I go ahead and start discussing about the importance behind the analyzing an algorithm, let's try to understand what an algorithm is. So before I show you my definition of what an algorithm is, can anyone tell me what do you think is an algorithm? Yeah?
Yes,
Anyone
sir.
who wants to come? Yes, please go ahead.
Sir, it's a sequence of steps that is required to solve any particular problem, computation
Okay.
problem to be specific.
Quite good. Okay.
Thank
So
you,
you
sir.
say that you are an algorithm contains or consists of a sequence, right, of instructions, right? That
Yes,
if
sir.
you follow would solve a particular problem that we're interested in, right, Nakina? Yes. Okay.
Yes, sir.
And that's correct. That's what an algorithm really is. Okay. So let's see a little bit more. Okay, let's see this algorithm. This is pretty much what you have said, but I have some more information here. But let's look at this one. So I am saying that an algorithm is a finite set of precise instructions for performing a computation or for solving a problem. Okay, sir? Okay, now when you look at this definition, you understand and you see there are some properties that an algorithm has. So first of all, an algorithm comprises of a set of precise instructions. So it contains a set of precise instructions. So you have got instructions, step 1, do this, step 2, do that, and so on, right? Now you have a set of precise instructions, okay? And what is the purpose of this set of precise instructions? The purpose is if you follow it, you are going to perform a computation or you're going to solve a problem that you're interested in. So basically, an algorithm is therefore can be referred to as a problem solution technique. Right, Nakina? So it's a solution technique of a particular problem. So it is not algorithm ta emon na je algorithm ta it starts everything, well, algorithm that just there is an algorithm like that. Algorithm, you have an algorithm because you intend to solve a problem, right? So first thing that you have is a problem. Now once you have a problem, You want to solve that problem. And so if you want to solve a problem, you have a solution technique. So this solution technique is what an algorithm is. Am I clear, Nakina? Yes?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So what does an algorithm contain? It contains a finite set of precise instructions. So it contains a set of precise instructions that if you follow would solve that particular problem that you're interested in. And this set of precise instruction must be finite. Okay, that's also another very interesting thing that you can see. So you have got a finite set of precise instructions. So you cannot have infinite set of instructions, right, Nakina? You have countable or finite set of precise instructions. Is it okay, Nakina? Yes?
Yes, sir.
Okay.
Yes, sir.
Now, an algorithm also has certain properties. Okay, so we can see certain properties here. The very first property you can see is that an algorithm must produce a correct result. It cannot happen that you have an algorithm, you follow the algorithm correctly, and then for a particular given input, it results in an output that is different from what you expected, right? It cannot happen. It must always produce correct result. Am I clear, Nakina? Is that okay? ঠিক আছে?
Yes, sir.
Okay.
Yes, sir.
So it cannot happen that it's producing some incorrect result. Okay. A good example of an algorithm could be if you can think of, let's say you want to cook something. Okay. Let's say you want to cook pizza. Okay. So you want to make pizza. So, and you have no clue of how to make a pizza. So what you do is you open up a recipe, right, Nakina? And what does a recipe contain? Anybody?
Ingredients.
Well, ingredients, yeah, it names the ingredients. So ingredients are like the inputs, right, Nakina? Yeah, so it names the input.
Yes.
And it also contains the set of instructions, right, Nakina? Kuntar por ki korte hobe. Am I correct, Nakina? Yes?
Sir, the procedures.
Right. So the idea is if you follow the set of instructions correctly, you will get the desired output. Can it happen that you are following the right recipe? You are following the right recipe, but surprise, surprise, you followed that one, but instead of pizza, you got a pasta. Can it happen? It cannot happen, right, Nagina? So an algorithm must always produce a correct result. That's very important, right? If you follow it correctly, if you have executed it correctly, then it should produce a desirable result. Is it clear, Nakina? Okay.
Yes, sir.
Second very important property of an algorithm is it must finish in some finite time. So your algorithm cannot go indefinitely. So it must stop. It must finish in some finite time. Is it clear, Nakina? Yes? Makes sense?
Yes, sir.
Yes, sir.
And the third important property that an algorithm has is that, as I said, as we discussed a little while back, that an algorithm is a solution technique, right, to a problem. Okay. Now you need to be able to, express this solution technique in some possible way. Okay. So it turns out that you can express an algorithm in a number of ways. You can express an algorithm in the form of a pseudocode. That's one way you can express it. You can express an algorithm in the form of a flowchart, or even you can express an algorithm in the form of an actual code. Is this clear, Nakina? Yeah?
Yes, sir.
So there are multiple modes by which you can actually express an algorithm. Is it clear, Nakina? Yes? Agreeable?
Yes, sir.
In this course, we mostly would express the algorithm using pseudocode. That's what we're going to do. Okay? But bear in mind that there are other ways you could also express an algorithm. Okay? All right. Now, so if we think what an algorithm is, you can think of it like this way. An algorithm, yes, it contains a set of precise instructions that you follow, okay, to solve a particular problem, right? Yeah. So when you follow the set of instructions, what an algorithm produces, it always produces some sort of output. Am I right, Nakina? Yes?
Yes, sir.
So an algorithm can take some input, process that, and can produce some output, right? Now, for some problem, it can so happen that you do not need any input at all, okay? But an algorithm must always produce or generate some sort of output. Is it clear, Nakina? Yes?
Yes, sir.
ঠিক আছে? Okay? Right. Okay. So that's there. Now, so any questions so far?
Yes, sir. I have a question.
What question do you have now?
Sir, why did they tell about precise? I did not understand that, but precise is related to measurement, right?
No, precise or opposite of vague. You cannot have
Oh,
any instructions
spot-
which is vague. ঠিক আছে? You
Okay,
cannot
clear.
say, yeah, you know, you do this or that depending on your mood. ঠিক আছে? So you cannot have something like that. It has to be precise. ঠিক আছে? Okay? All right?
Okay, got it, sir.
Good. Okay. Any other questions anybody has? No. Okay. Fantastic. Okay. The next thing we would like to discuss, and this is very important that you understand this. You see, do you think algorithm is an old discipline, or do you think an algorithm is a new discipline? What do you think?
An old one, sir.
How
Old.
old? How old do you think, and how old do you think is this discipline? I mean to say, when do you think was the first algorithm written?
Sir, I think it's from the Aristotle era, so like around 2200 years.
2200
Sir,
years.
quite old.
Okay. Acha. All right. Anybody else with any other thoughts about that? No. But you all agree that it's a pretty old discipline, right, Nakina? Yeah. Okay. All right. It's indeed a pretty old discipline. So I'm going to give you a very brief timeline. And by brief timeline, I mean it's a very, very brief timeline. It is not possible for me to write down all algorithms in the timeline because there's just so many. Okay. It's impossible. But I'm going to give you some very brief timeline. And the whole point of giving you this timeline, so this actually, you know, as a student of computer science, you must be aware, like you must be aware of the history of it a little bit. Okay, this is for your scholarly aptitude. I will never ask these questions in the exam, but I think these are important things to also, you know and ponder about. Okay, so the first documented algorithm. Now, I believe there were algorithms before that time as well, but the first documented algorithm that we know of came in 1600 BC. So now I hope you can see how old this old is this discipline, right? The first documented algorithm we have is in 1600 before Christ, right? Yeah. Okay. Where the Babylonians, okay, they developed algorithms for factorization, and for finding out the square root of a number. So they developed algorithms by which they could find out the square root of a number, or they could actually factorize an expression. Yes, and this was something that was developed in 1600 BC. Now, mind that there could be algorithms before that time, and I suspect that there are algorithms before that time as well, but somehow they were never documented, or well, it's not within our reach. It's just not there. The documents are not there, so we could not trace back. The historians could not trace back. Okay, so the oldest document that we have about algorithm dates back to 1600 BC. But that indeed also tells you how old and how rich this discipline is. Okay, and that's the reason why when some students actually, if you think that a course eto keno jinishpotro, it's just because it's such a rich discipline. There's just so many things. Okay, right? That's the point. Now, let me also highlight some of the algorithms that you may have heard of. So just to give you a very brief timeline of that. Have you ever heard of the Euclid's algorithm? Yeah, quite famous. Have you heard of that?
Yes,
No?
sir.
Yes, sir.
Yeah.
Yes,
What
sir.
is it used for?
Sir, prime number
Or is it
factorization.
for GCD?
No, not for factorization. This
Or is it for the GCD?
Yeah, GCD. It's used to compute the GCD of two numbers. To compute GCD of two numbers. Okay, And how do you compute GCD of two numbers is something that is as old as 300 BC, as you see over here, right, Nakina? To compute GCD of two numbers. Okay. Now, have you ever heard of the series of Eratosthenes?
Yes, sir.
जी सर
Yes, sir.
प्राइम नंबर
Yeah.
जनरेट करता हूँ
Yeah. Some
Prime-
of you may have heard of this one, especially those people who have done some sort of, competitive programming or programming contest.
Yes,
যারা
sir.
কাজ করেছে, they
Yes,
may
sir,
have
yes.
heard of this one. But do understand, this is a very, very old algorithm. It was
Yes,
first,
sir.
it's a 200 BC algorithm. ঠিক আছে? So old. ঠিক আছে? But still, I mean, we use it, right, Nakina? Yeah? Okay.
Yes, sir.
So this is just to give you some ideas about how old this discipline is, okay? How old and rich. Okay. In 628 AD, we have something called the Chakravela method that was described by Brahmagupta. Okay, don't worry about that. Okay, here's a very interesting time. Okay, 820 AD, that's about the 9th century, right, Nakina? Yeah. In
Yes,
the
sir.
9th century, we had a Persian mathematician over here called Al-Khwarizmi. Okay, he developed algorithms for solving linear equations and quadratic equations of algebra, right? Algebra the linear equations, quadratic equations, right, Nakina? Yeah. And how do you solve them? This algorithm was designed in the 9th century, 820 AD, by this Persian mathematician called Al-Khwarizmi. Now, the reason we highlighted this particular date is not because of that he discovered, algorithms for solving the linear and quadratic equations, but rather this is a very interesting time because Al-Khwarizmi actually happened to be a very, charismatic person. Okay? Now, mind that before the time of Khwarizmi, there were algorithms, right, Nakina? There were algorithms, right? Okay. But it is Al-Khwarizmi who actually popularized the concept of algorithm. Okay? He actually was a very charismatic person. He actually did a lot of work. He documented a lot of historical work of algorithms. Okay, and he made it available and reachable to a lot of people. Okay? And so that's how he actually popularized the whole idea of algorithm, right? Okay, and it is after his name we call it algorithm. So the word algorithm is actually derived from this Persian mathematician called Al-Khwarizmi. Is it clear, Nakina? Yeah.
Yes, sir.
Okay.
Yes,
Yes,
sir.
sir.
Now, around the similar time, 850 AD, you see, similar time, the 9th century, there was another Persian mathematician there called Al-Kindi. And Al-Kindi developed algorithms for cryptanalysis. Now, can anyone think about what cryptanalysis could be about?
So sending messages for what?
So it could be about cryptography and things like that, security kind of things, right, Nakina? Yeah.
Yes, sir.
So
Protecting data.
concepts that are so many, I would say, concepts that are so relevant in today's time. If you see very carefully, these were actually solved. Many people were interested in as old as in the 9th century even. And that's the great thing about algorithm. It is a very, very rich discipline, and these were in the form of algorithms and stuff like that. And when computer came in, all these ideas just fit into the computer. And the reason why computer actually, many people say that computer was one of the greatest inventions. Okay, yeah, it's true. It's one of the greatest inventions in recent time. True, but one of the reasons, one of the facts that made it so, success was because we had so much background work of algorithm that has happened for such long time. Okay, right? That's the whole thing. Now, there are some algorithms that you'll be learning in this course. Like, for example, let me name some of them. Like, for example, you learn about merge sort algorithm in this course. You learn about Huffman coding. I hope I will have the time to complete that. Then Kruskal's algorithm, Prim's algorithm, Bellman-Ford, Dijkstra, Quicksort, Hipsort. We'll learn all these algorithms, and that's why I also wrote the year when these algorithms were invented. Like, for example, merge sort algorithm, invented in the in 1945, in the year when the Second World War came to end, right? Huffman coding, well, this is a data compression algorithm, right? You may have heard of that, Huffman coding. Have you?
Yes, sir.
Some of you may have, some of you may not have. That's okay. And this data compression algorithm was actually invented in 1952. Okay, all right, by David Hoffman. Okay, then we have got Kruskal's algorithm, Prim's algorithm. So we will learn all these algorithms that I just put a tick over here. Okay, and now if you see that, you might, it might come to your mind, and you might say, are we all learning the algorithms which are so old? It turns out that these algorithms are very, very important in today's context as well. Because they stood the test of time. Okay, they're still very, 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 very important in today's context as well. Right? Okay, now clear? So yes, these are quite old algorithms. That's true, but we still use it a lot. Okay. Here are some more algorithms. You see, if you look at the timeline, for example, 1972. We have something called Graham-Scan algorithm that is used to find a convex hull. Okay, if you want to find the convex hull, that's what you use. Okay, then 1975. Okay, John Holland, he came up with an interesting idea called genetic algorithm. Now, genetic algorithm is a huge area. It is a huge area. In fact, if anybody wants to teach genetic algorithm, like, we will not be covering genetic algorithm. It's impossible. But if anybody wants to learn about genetic algorithm, usually you will get a senior level undergrad or master's course at the entire semester at the course based on genetic algorithm. Okay, 1978, this is a very interesting algorithm called LZ78. LZ78 is because it was invented in 1978. LZ by the two people who actually invented this algorithm, called Limpel and Zev. Limpel-Zev 78 algorithm. This is also a data compression algorithm. Okay. Okay, so here's a very interesting algorithm in 1976 called KMP algorithm. It stands for Knuth Morris Pratt algorithm. Okay, this is used for string matching. Okay, the string matching algorithm. Okay, now here 1998 PageRank algorithm by Larry Page. Anyone knows what is this algorithm about?
So Google search indexing.
Yeah, yes, exactly. Whenever you make a query in Google search engine, what happens? It finds a list of websites and it ranks them. In the order of relevance, right? The most relevant one at the top, right? So there's a PageRank algorithm, and this was in 1998. That's the time when the Google search engine was launched. 2001, there's an algorithm by Viola-Jones. It's called the Viola-Jones algorithm for real-time face detection algorithm. Okay, and right now in recent time we have more and more very, very interesting algorithms. So that's just a very brief timeline given to you to show you how old and how rich this discipline is. Right, clear? Yeah, I hope you get the point. Right,
Yes, sir.
Okay. Now, as I mentioned a few slides back, I did say that you can express an algorithm in a number of ways. You can express an algorithm in the form of a pseudocode. You can express an algorithm in the form of flowchart, or even if you wish to write an actual code, you can do that using a language of your own choice. So here's an example. Okay. The problem that we have, I'm just going to give a very simple problem. And the problem that we have, it says that find the sum of 5 numbers. So you're going to take 5 numbers from the user and you're going to actually sum them up and print that number out. So it's a very simple problem. Anyone can solve this one, right? Okay. So what you do is you will be asking the user to provide an input 5 times, right? One, twice, third, fourth, and fifth time. Every time the user gives an input, you sum it up. Okay, and then you produce the sum of all the 5 numbers. numbers, right, Nakina? That's what you're going to do. Correct? Am I clear?
Yes, sir.
Okay, so that's the idea, that's the solution. But now what you have to do is you have to actually, um, you have to express the solution, that you just express the idea that you have right now. Okay? So that's algorithm. So you can express algorithm in many ways. You can express the algorithm in the form of a flowchart, which you can see over here, right, Nakina? So if you see the flowchart, you start, okay, and now you have got two variables called sum and count, and you initialize them to 0. Is that okay, Nakina?
Yes, sir.
Then you're taking an input from the user. So you're doing an IO operation here, input output operation. So you're taking an input, and whatever the input the user is providing, you're storing that value into a variable called n. Is that okay, Nakina? Yeah?
Yes.
Yes, sir.
Okay. After you have stored that value into the variable called n, so then you have to sum it up. So the new value of sum is sum plus n. So initially it was 0, 0 plus this n. This is stored in sum, right? And the count has incremented by 1 because you have read it once. So count equals count plus 1. Okay. And then you check, is count smaller than 5? Now, if the count is smaller than 5, that means you did not read up to 5 numbers. So you're going to go ahead and take the input again. Okay, once you've taken the input, store it in n. Okay, update the sum, increment the count, and again you're going to check. So you keep on going until you have already read 5 numbers. Once you have read 5 numbers, then count would be equal to 5. So count is not less than 5. So this decision would be no, right, Nakina? So you go there and you print the sum value and you stop. Is it clear, Nakina? Yes.
Yes, sir.
So that's the idea that you had, right? And we express the idea using the concept of flowchart, right, Nakina? Yeah. So we can express an algorithm in the form of a flowchart. Are we good, Nakina? Yeah.
Yes,
Okay.
sir.
So we can also express the algorithm in simple English, which we call as pseudocode. Okay, pseudocode. Now, what does the word pseudo mean?
Lie.
Answer.
False.
Yeah, pseudo like false bolte pare anake, like bolte pare. It's like a code, but not really an actual code.
Actual code.
Actual code to na, but like an actual code, right? So you write it in simple English, plain simple English. Okay. So if you see here, I can do that one as well. So the first step is you initialize sum and count to 0. So that's what you write. Initialize sum is 0 and count equals to 0. Done. Okay. Second, next after that, you take an input from the user and store it in n. So you can say enter n. So that's an IO operation. Okay. And then you're going to update the sum and increment the count. So that's what you do in step 3. Find sum plus n and assign that value to sum. So the new value of sum is sum plus n. And you increment the count by 1. Is it okay, Nakina? Yes?
Yes, sir.
Okay. And then you're going to check what is the count value smaller than 5 or not. So you're going to check that one. Is the count value smaller than 5 or not? If the answer is yes, you need to go back to enter n, which is step 2. So if it is yes, go back to step 2. That's what you're going to do. If it is no, then what you're going to do, okay, you're going to go here and print the sum. So otherwise, you're going to go print the sum and that's it, done. Clear, Nakina? Is that idea okay?
Yes, sir.
So
Yeah.
pseudocode-টা কি স্যার আমরা ফ্লোচার্ট দেখে করি?
Sorry, say that again.
সুডোকোড যেটা আছে স্যার ওটা কি স্যার ফ্লোচার্ট দেখে করতে হয় নাকি স্যার?
Oh my goodness. Well, you don't have to. But the reason why I did it is because I'm saying a flowchart corresponding pseudocode would be this one. Right, Nakina? Yeah?
Yes, sir.
That's why I just compared. But you don't need to. If you're writing a pseudocode, it's not that you have to draw a flowchart and write down the pseudocode. No. Okay? These are two different ways of expressing the algorithm. Am I right, Nakina? Yeah?
Yes, sir.
Okay? All right. Okay. So the answer to the question, যে আমার কি pseudocode লিখতে গেলে কি flowchart করে তারপর ওটা দেখে করতে হবে? না, you don't have to. ঠিক আছে? Okay? But here I'm expressing the same idea using the flowchart as well as using the pseudocode. So I was comparing. Okay, clear? Is that okay?
Yes, sir.
Okay.
Yes, sir.
Now, here's a question for you. Let's see how we solve this problem. Okay, remember, before you write any algorithm, now some people have this habit is whenever I give a question, they just straight jump into code. Don't do that. Okay. All right. Pause a little bit. Whenever I give a question, first of all, understand the question. Okay, because whenever you are going to write an algorithm is a solution technique to a problem. So because it's a solution technique to a problem, you must understand the problem first of all, right, Nakina? Yes. Once you have understood the problem, then design your solution. And for that you need a pen and paper as well. Think about the solution. Once you're certain about the solution, then go ahead and write down the code if you like. Clear, Nakina? Is that okay? All right. So don't jump. Okay. So here's a question we have. I want you guys to think about this question. Okay. The question says, can you come up with an algorithm to compute the GCD of two numbers? So the input is we have got two numbers. So the problem is this. So if I could express the problem is like this. So what we want to do, we want to take two inputs. So let's say, okay, the inputs are I and J, and I want to we want to come up with an algorithm which will determine the GCD of these two inputs. Am I clear, Nakina?
Yes, sir.
So now the question is, so you have to take two inputs, I and J, okay, and you want to write an algorithm that will produce the GCD of these two inputs. Okay, is that clear? I hope the question is very clear, right, Nakina? Yeah. So now the question is, how do you find a GCD of two numbers? So let's take an example. Let's say I is 12, J is 18. Can you tell me what is the GCD of 12 and 18?
6.
6. How did you find that out?
Sir, we divided it with from 2 to 6, and then basically after 6 we can see that we cannot divide it anymore. So 6 plus is the largest one. We can also do the same by multiplying the lowest common factors.
স্যার 12 আর 18 এর যতগুলো ডিভিজন আছে তাদের মধ্যে কমন ডিভিজন যেটা তার মধ্যে সবচেয়ে গ্রেটেস্ট যেটা ওইটাই GCD.
Well, okay, fine. That could be also a way of looking at this. So there are many ways I could find out the GCD of 12 and 18. So one of the ways that someone was saying, last Jini Bochilan, he said, okay, we can go by the definition as well. GCD stands for greatest common divisor. So let's find out the divisors of 12 and 18. So let's write them down. Divisor. Now, what do you mean by divisor? Divisor means those numbers that will divide this one so that there is no remainder. So can you tell me what are the divisors of 12?
2.
1, 2,
3, 4,
yes, then
6,
6,
12.
anything else? 12. Anything else? No.
No, sir.
Okay. Acha. Now what are the divisors of 18?
1,
1, 2, 3,
1, 2, 3,
1, 2, 3,
6,
9.
6,
9, 18.
9, and 18. Right. So these are the divisors of 18. So we found that the divisors of 12 and 18. So now the next thing is you have to find the common divisors. So if you look at the common divisors between 12 and 18, 1, 2, and 3 are common. Can you see that here? As well as 6 is common, right, Nakina? Yes?
Yes,
You
sir.
get it?
Yes,
So
sir.
if you look at here, the common divisors of 12 and 18. So common divisors of these 12 and 18 would include the 1, 2, 3, and 6. Am I right, Nakina? Yes?
Yes, sir.
And
Yes,
what
sir.
does GCD stand for? GCD is the greatest of the common divisors. So of these common divisor, which one is the greatest? Which one is the largest?
6.
6. So that's the GCD of 12 and 18. Clear, Nakina? Is that okay?
Yes, sir.
Yes, sir.
Yeah. So that's how you find out the GCD of two numbers. I hope that makes sense to all of us, right, Nakina? Yes?
Yes,
Okay.
sir.
Yes, sir.
Achha. There are many other techniques that we have to compute GCD. For another technique that you might have learned in the school could be you try to divide 18 by 12. The 12, 1, 12. There's a remainder. Sorry, there's a remainder of 6. And then you bring that 12 here. 6 times 2 is 12. And that's it. There is no remainder. Hence, this 6 must be the GCD. Have we learned something like that in the school as well?
Yes, sir.
You have. Okay. So, the fact is there are many techniques to compute the GCD of two numbers. Okay. All right. So let me show you another strategy that we can use to compute the GCD of two numbers. Okay, sir? And this is a very interesting strategy, I think. Okay. So let's see what's the strategy. The strategy is this. So we have got 12 and 18. So I'm going to write it down. So I is 12, right? And J is 18, correct, Nakina? Okay. And what you're going to do is you're going to keep doing what I'm going to tell you until I and J becomes equal. So first of all, look at this one. I and J, are they equal or not equal?
Not equal.
Not equal. So which one is the larger one, I or J?
J.
J. So you're gonna update the larger one. How are you going to update this one? You take the larger value, which is 18, minus you take the smaller value. So what is 18 minus 12?
6.
6. And you update that as the new value of J. Is it clear, Nakina? Yes? Okay. And you keep doing this one until I and J becomes equal. So let's see again. Is I and J equal now? No, because I is 12 and
No,
J
sir.
is 6. So which one is the larger right now?
I.
So let's update I. So what would be the new value of I? 12
6.
minus 6.
6.
12 minus 6 is 6. Right, Nakina? Yeah?
Yes,
Now
sir.
you can check I and J. Are they equal now?
Yes, sir.
Yes. And because you found them equal, that's the GCD of 12 and 18. Okay? That's a very interesting technique, right, Nakina? Yeah? And it always works. So let's just take another example just to make sure that it works or not. Okay, so can you give me 2 more numbers? And we'll just try 2 more numbers. Give me any 2
Sir,
numbers.
64 and 18.
64 and 18. So I is, let's say, 64, J is, let's say, 18. Last time I was smaller and J was larger. So this time I take I is larger and J is smaller. Doesn't matter. Now, before I go ahead and do that, can you tell me what is the, GCD of 64 and 18? What would be the GCD of 64 and 18?
2.
2. Is it so? Okay, let's check. Okay, let's use our strategy.
2 boy.
Okay, 60. Okay, তার মানে এখন অনেকগুলো iteration হবে, but let's see, you chose that. So দেখা যাক. 64 and 18, which one is larger? 64 is larger.
64.
So 64 minus 18, how much is that?
46.
46. So the new value of I is now 46, right? Okay, 46 and 18, which one is larger? 46. So let's say update the value of I. So 46 minus 18, how much is that?
28.
28.
28, okay. 18 and 28, which one is larger?
28.
28. So the updated value should be 28 minus 18, which is how much?
10.
10.
10.
10 and 18, are they equal?
No.
No, not yet. So which one is larger?
18.
18.
18.
So what's the new value of J?
8.
8. 18 minus 10, which is 8. 8 and 10, which one is larger?
10.
10. So what's the new value of I now? 10 minus 8, which is how much? 2.
2.
Okay. Now let's see this one. 8 and 2, which one is larger? 8. J is larger. So the new value of J is 8 minus 2, which is 6. Again, J is larger.
4,
6
2.
minus 2. Sir, okay. I get it. You can subtract well. 4, and then 4 minus 2 is 2, and now you see they become equal, and there you stop, and you have found that the GCD of 64 and 80. Correct, Nakina? Clear?
Yes, sir.
Yes, sir.
Okay, so are we convinced that this approach works?
Yes, sir.
Yeah, this works, right? So
Yes,
now when we are convinced about the approach that we have, when we are convinced that yes, this works, now it's a good idea to actually write down this as in the form of a algorithm, right? So I want to actually write down the solution in the form of an algorithm. So what can I do? So here's the name of the function, that's a GCD, and we're taking two, values, one stored in I, another stored in J, right, Nakina? Yes?
Yes, sir.
And
Yes,
what
sir.
are we going to do? We are going to run a loop, okay, until I and J becomes equal, right, Nakina? Yes?
Yes, sir.
Okay, so the loop is going to run. So I'm going to run a loop while I is not equal to J, right, Nakina?
Yes, sir.
Yes, sir.
Okay, and what we're going to do inside the loop, we're going to check which one is larger. That's it. The I and J যদি equal now high, I'm going to go inside the loop. So one of them would be larger, either I or J. So if I is larger than J, yeah, so the new value of I would be equal to what? I minus J.
I minus J.
Otherwise, else, I'm going to update J, which will be equal to J minus I. Correct, Nakina?
Yes, sir.
Yes, sir.
And that's what you're going to do inside the loop. And once we're done, we come out of the loop, and what we're going to return. When we come out of the loop,
I is equal to J.
I and J both are equal. So you can return any of them. It's fine. So let's just return I. So that's good enough. Is it clear, Nakina?
Yes, sir.
Yeah? Does it make sense to everyone?
Yes, sir.
Yes,
Yeah.
sir.
So this is a simple algorithm to compute the GCD of two numbers. Are we good? Okay. Just give me 1 minute time. Let me put my laptop on charge, and then I'm getting back to you. Okay, so is this solution okay to everyone? Yeah.
Yes, sir. Okay.
Yes, sir.
Okay. So
Yes, sir.
so what we have done is we have expressed the algorithm in the form of a pseudocode. So this is our pseudocode, isn't it, Nakina? Yes. Now, pseudocode and actual code, they can differ. That's fine. So if I want to write down the same idea in one using a programming language of our own choice, so let's say I want to write a code, actual code. Let's say I want to write a code in a programming language, like using a programming language like C, or let's say Java. It doesn't matter. They would have similar syntax. What do I do? So let me write it down. So I want to actually, write these pseudocodes. Protect a line, actual code level. So the function is called GCD. And what are the parameters we have? How many parameters we have?
IJ.
Two,
Two
sir.
parameters, I and J. But if we write it in C, we must write down the data type as well, right, Nakina? So int I
Yes, sir.
and int J. Correct, Nakina? Yes?
Yes,
Yes, sir.
Also, remember that this function will return an integer. So the return type must be also given over here. Is that right, Nakina?
yes, sir.
Yes, sir.
And then we must start with braces. So the braces say that, well, we started with this function. Inside the function, the first one is while I is not equal to J. So this is as it is. I'm going to write this one while I is not equal to J. Okay. And then if that's true, so we go inside the loop. And the first thing I'm going to check is this one, if I is greater than J. So this is as it is. If I is greater than J, then I'm going to update the I. The new value of I would be equal to I minus J. And there's a small syntax here. I must end the statement by a semicolon, right? Else, I'm going to update the value of j, which would be equal to j minus I, and I must end it with a semicolon. And then when we are done with the loop, when we come out of the loop, I will just return I, and that's it. Right, Nakina? Clear?
Yes, sir.
Okay.
Yes.
So you can see this is the pseudocode, and this is the actual code, right? Nakina, using languages like programming languages like C or Java. Okay? Now, what can you see? Okay, as the difference between these two codes. What are the differences that you can see? First thing that you can see over here, in the pseudocode, I did not write any data type here. Right, Nakina?
Yes, sir.
In the actual code, there was data type mentioned over here. So my question is, why did I not write a data type in the pseudocode? Any idea?
অ্যাকচুয়ালি স্যার এটা লং লং হতে পারে, এই জন্য লেখেন না।
লং লং হলে তো এখানে লং লং লিখতে পারি।
স্যার আমরা
pseudocode এ মেমরি অ্যালোকেট করতে হচ্ছে না।
স্যার আমরা অ্যালগরিদমটা যে ইমপ্লিমেন্ট করবে ওদেরকে একটা ফ্রিডম দিচ্ছি যে ওদের মতো করে ইমপ্লিমেন্ট করার জন্য।
আচ্ছা, ওকে। সো
because it is like code, but it is not actual code. It is a representation of what the code will be. So it is not necessary to state what the data type would be.
But the main reason behind this is, in a pseudocode, we are not. So pseudocode is not any, it's not specific to any programming language. Am I right, Nakina? Yes.
Yes.
It's a type paper, right?
Yes, sir.
এই যে data type গুলো লিখছি, int here, and int here, this is specific to these languages that we have chosen. There are many other programming languages that we have where we do not need to write this data type. One example would be Python. So if you are holding this one using Python, you don't need to write this as int, right, Nakina? So whether you write it as int or you don't write it as int, it is specific to the language that you're choosing. But in a pseudocode, we are not writing this as a specific to a particular language. So we usually typically ignore those things. Is it right, Nakina? Okay. Similarly, things like here semicolon dawa hoyeche, but we did not give any semicolon here because that's also something specific to those languages, right, Nakina? Clear? Is that understandable? Yeah.
Yes, sir.
Okay. Now we have given some braces over here, and here. We have given some braces here and here, but we did not give any braces over here. That's also fine. Okay. Right? Giving the braces is also specific to languages. There are many languages where you do not need to give any braces. Okay. So that's also specific to a particular language. Now you might say, কিন্তু আপনি তো indent করেছেন। I mean, what if I don't indent that? That's fine. So even if you do not indent in a C language, your program would still compile. So indentation is done for good readability of your code, right, Nakina? Yeah? Yes? Clear? Okay. So when you are writing a pseudocode, you do not need to be specific to any particular language. Now, এখন যদি কেউ যদি এখানে একটা braces দিয়ে দেয়, it's not going to be wrong. So you have the liberty to doing that. But remember, we write pseudocode as to express the idea of the solution. তারপর এটা পরে যদি যে এটাকে implement করছে, he can implement it any language of his or her own choice. Is it clear, Nakina? Yeah?
Yes, sir.
That's it. So we understand that. Okay. Does anyone have any question at this stage?
Yes, sir.
What is
Sir.
the question?
Sir, we termed the code written using C or Java as function. So what we term the code that is written in pseudocode?
Oh, it's okay. You can like, it's up to you. You can call it a function as well. It doesn't matter. Okay. You can call it a function. Some people tend to call it by other names as well. For example, let me show you. So it
Sir,
doesn't
I
matter.
also
So
read
for
it
example,
to be named as module.
You can, if you want to say it is a module, so
Or
I would not
procedure.
say যে এটাকে স্পেসিফিক কোনো নাম দিতে হবে। যেমন আমি একটা এক্সাম্পল দিই। So here's a different language, different kind of things. Okay, let me just show you so that you'll understand that. Okay. So you see, this is written in a different code, so don't worry about that. Some people call them as procedures. These are the different procedures. Clear? Yeah. So let's
Yes,
say I
so
go
that
to
is
the
what was
procedure list.
referring to.
So this is what's called procedure. So you can call it a procedure as well. So it's fine. Okay. But if you call it a function, it will not be wrong. Is it clear? Okay.
Yes.
Okay. Acha, here's the second problem, but I'll just leave it to you for you to think about it. I'll ignore that for the time being. Okay. So far, are we good enough? Aturu clear, Amander?
Yes, sir.
Yes, sir.
Good. So let's go back to square one and let's think. Let's think a little bit. Okay. What are we doing in this course? What is this course about? Remember, this course is called the design and analysis of algorithms, right, Nakina? So the fundamental things that we do in this course is we try to we study the design and analysis of computer algorithms in this course. Okay. Remember what are the basic goals of an algorithm? So let me give you some more, goals that an algorithm could have. So whenever you write an algorithm, we have certain goals for an algorithm. Number one, the algorithm must be always correct, right, Nakina? Yes, agreeable?
Yes, sir.
Yeah, the algorithm must always terminate. Agreeable?
Yes, sir.
Okay, and there is another important thing that an algorithm must also have, which we did not state earlier, but we're going to state from now onward, which is it should perform well. It must have good performance. Now, what if I write an algorithm whose performance is poor? Will I call it an algorithm? Yes, it's fine. You can call it an algorithm. But if it's a poor algorithm in terms of its performance, then what happens is, it doesn't become very usable, right, Nakina? Yes? Clear?
Yes, sir.
Okay. So, কোন একটা algorithm যদি poor performance থাকে, I would not label it as a not algorithm. It is still an algorithm, but that particular algorithm may not be actually, suitable for use. ঠিক আছে? এটা দেখা যায় যে এটা usually খুব একটা use করা যাবে না. Is it clear নাকি না? Agreeable with that নাকি না? Okay.
Yes, sir.
So this is something we want to concentrate now. So along with these basic properties, we want an algorithm to perform well. Right, Nakina? Yes, because if an algorithm does not perform well, then its usability becomes a question. Okay, so that's why I've written over here. Performance often draws the line between what is possible and what is not possible. So if you have a poor algorithm, well, it's fine. Your algorithm might be correct, but it may not be very much usable. It may not be something that you can use to do something. Yeah. Okay. So that is something which is very, very crucial to us. So now, in the next few slides, what we're going to do, we are going to elaborate on this idea. We're going to discuss why performance is so important. And I'm going to hopefully at the end of today's class, I'm going to give you an example by which we see why performance is so important to us. Is it clear, Nakina? Yeah. Okay. So let's look at this one. So now I like the title of this course a lot. That's why probably in many of my slides you see that I do write the title of this course, because the title of this course actually tells us what we're trying to do over here. Okay. Now let's try to see this one. Okay. Let's say you write an algorithm. Here's your algorithm. You write some algorithm. Now, when you have written this algorithm, maybe this algorithm is not going to use any resources, right? Yes? Okay. Now, once you have written an algorithm, let's say you implement this algorithm using a programming language. Yes, Nakina?
Yes, sir.
When you write this, when you implement this algorithm using a programming language, you have a code, right, Nakina? Yes?
Yes, sir.
We also call it the program. You have a program. Am I correct, Nakina? Yes?
Yes, sir.
Yes, sir.
Let's say when you're executing this code, then what do you call this one?
Instruction.
No, a program already contains instructions. Take it, okay? But when you're executing the code, that means this is a program in execution. Now this has a name. Does anyone know the name of that one? Is there anyone over here who has done CSC 323 operating system? করেছেন না অনেকে আছেন না এখানে অপারেটিং সিস্টেম করেছেন? Okay, for them, do you remember when you have executed a code, a program in execution, it has a name. What is that?
Running.
Oh no, this is called a process. Okay, it's now called a process. ঠিক আছে? Is it clear nakina? Yes? All right? ঠিক আছে?
Yes, sir.
Okay, now when you are running this program, okay, all right, when the program is in execution, ঠিক আছে? Okay, now this process, we call that as that's also a program, but we just call it a process. ঠিক আছে? Why do we call it a process? Because it's just a program, but along with the program, it also requires some resources. Am I right, Nakina? Yes?
Yes, sir.
So a program in execution requires what?
Resources.
Resources. Yes, it requires resources. Yes or no?
Yes, sir.
What kind of resources does it require?
So CPU time, RAM, could be IO.
Yeah, so there could be a lot of resources it may need. So, but the typical resources it might need include space or memory, right? It might need some memory, Nakina. Yes?
Yes, sir.
Yes, sir.
And also time, right, Nakina?
Yes, sir.
Okay.
See, sir.
Now, depending on what kind of program you have written, it may need other kind of resources as well. For example, it may need, I don't know, communication bandwidth, for example. It may need to use some, somebody said IO, it may need to use some, let's say a network printer or something like that. So depending on what kind of program you have written, it may require other resources. But most programs that you write would require these two resources at least. Clear, Nakina? All programs would require these two resources at least, which is space and time. Is it okay?
Yes, sir.
এখানে কনফিউশন থাকলে একটু বলেন আমাকে, I would like to clarify. Is it okay, Nakina? Yes? So far so good?
Yes, sir.
Yes, sir.
ঠিক আছে? এটা তো সবার ক্লিয়ার, রাইট? যে স্পেস এন্ড টাইম আর রিসোর্সেস, রাইট Nakina? Yeah?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So that means whenever you're running a code, it requires computational resources. Am I clear, Nakina? Yes? Okay. Now, when we are going to analyze the code, okay, when we are going to analyze the code, the purpose of analyzing a code is to predict the cost of an algorithm. Now you might say, well, does an algorithm have a cost? Of course it has a cost. Isn't it using resources? If it's using resources, it's incurring cost, right, Nakina? So you measure the cost of an algorithm in terms of the resources that it uses, right, Nakina? Yes?
Yes, sir.
Okay. এখন যদি এমন হয় যে two people come up with two different algorithms, okay? Algorithm A and algorithm B. Now দেখা যাচ্ছে algorithm A, it takes low space and low time. ঠিক আছে? Let's say that's what happens. And let's say algorithm B takes high space and high time, or large space. Okay, let's say I wrote high space and long time. ঠিক আছে? Which one would you prefer, algorithm A or B?
Algorithm
Yes,
A.
But
You
the one
prefer
controlling the
algorithm A,
cost.
right, Nakina? So you always like the one which is less costly here, right, Nakina? So analyzing an algorithm allows you to understand what is the what kind of resources is this particular algorithm using. ঠিক আছে, Nakina? Okay, so we predict the cost of an algorithm in terms of the resources during the analysis phase. In the designing phase, let's say whenever we want to write an algorithm, ঠিক আছে, our objective is always to find algorithms, or our objective is to always design algorithm such that it is an algorithm with the minimum cost, right, Nakina? Clear?
Yes, sir.
ঠিক আছে, এতটুকু সবাই ক্লিয়ার নাকি না? সবাই ক্লিয়ার না? কারো কোনো
Yes, sir.
কনফিউশন আছে? Okay,
Yes,
so
sir.
that's basically the purpose that we have now. Okay, good. So we have understood a lot. Now I want to give you an example. I want to give a hypothetical example. And using this example, I would like to show you why this is important. Why is it important that we analyze an algorithm? Okay, let's take an example here. And analyzing an algorithm, let's say we try to look at why an algorithm that uses low resource is important to us. Okay? So that's a very important question, and we would like to answer this one using an example. Now, all of us agree with that. No? If you have an algorithm that uses low resources, that's a preferable algorithm, right? Yeah, we all agree to that. But let's just take an example and try to see what difference does it make. Okay? All right. Here's an example for you. So I'm going to give you a very fictitious example. And in my fictitious example, we have got two friends here. And these two friends are called Alice and Bob. Nakina? Yeah?
Yes, sir.
So we have got two friends, Alice A, Bob B. Ebong, we give a problem to these two friends. We give a particular problem to these two friends, and we ask them to come up with an algorithm to solve the problem. But the challenge is they are not going to work together. They are going to work independently. Okay? So Alice and Bob are going to work independently, and they will come up with two different solutions to a problem. And what's the problem that we're giving? They are given the task of writing an algorithm that can sort some 10 million numbers. ঠিক আছে? তার মানে কতগুলো নাম্বার দেওয়া হয়েছে তাদেরকে? কতগুলো ইন্টিজার্স দেওয়া হয়েছে?
10 million.
10 million.
10 million. 10 million is 10 to the power 7. So the input size n is 10 to the power 7. Is it clear, Nakina? Yes?
Yes, sir.
Yes.
Okay, so we have given them an input of size 10 million, and we ask them to write an algorithm that will sort these 10 million numbers. Yes? Is that okay?
Yes, sir.
Yes, sir.
Yes,
Okay.
sir.
So there are two things that we have asked them. Number one, write down an algorithm. Okay, that would do that. And number two, implement this algorithm. Okay. All right. So let's see what Alice has done. Alice writes an algorithm, and what does the Alice's algorithm do? It takes some 2n square instructions to solve the problem. কতগুলো ইনস্ট্রাকশন লাগে তার প্রবলেমটা সলভ করতে? Alice?
N square.
2n square.
2n square. N square কেন বলছেন স্যার? লেখা আছে 2n square.
2n
Okay.
square.
2n square. What is n?
10 to the power 7.
10 to
Yeah,
the power 7.
n is the input size, right? Nakina, clear?
Yes, sir.
Yes,
Yeah.
sir.
Okay. So Alice writes an algorithm, and her algorithm takes twice n square instruction to solve the problem. Yes? Is it clear, Nakina?
Yes, sir.
Yes, sir.
Okay. So after she has written the algorithm, after she has designed the algorithm, she implemented the algorithm using her computer. Okay? So she implemented the algorithm using her computer, and the computer that she uses executes 10 billion instructions every second. That means this computer that she uses executes 10 billion. 10 billion means 10 to the power 10, right? 1 billion is 10 to the power 9, so 10 billion is 10 to the power 10. So this executes 10 to the power 10 instructions per second. That means every second 10 to the power 10 instructions are executed. Clear, Nakina?
Yes, sir.
Okay, got that. What about Bob? Bob writes a different algorithm. And Bob's algorithm requires some 50 n log n instructions to solve the problem. ঠিক আছে?
Yes, sir.
Okay. So is it more instruction or less instruction than that of Alice?
Less instruction.
Less instruction.
Less instruction. So if it requires less instructions, so car code better? Bob's code better and Alice's code better?
Bobber code, sir.
Bob's code, because it requires less instructions to solve the same problem, right? Yeah. But here's the twist. What is the twist? When Bob implemented his code, he used a computer which executes 10 million instructions every second. 10 million means 10 to the power 7 instructions are executed every second. So Bobber, the computer, the processor, is it faster processor than Alice or slower processor than Alice? Slower processor than Alice. So Bob writes a better quality code, but runs it on a slower device. Okay. So the question now is, which one eventually would run faster? What do you think? Which one would run faster?
Bob.
Why? How do you jump and say Bob's?
Sir, better algorithm.
Better algorithm, but it runs on a slower PC. Doesn't that have an impact? That also has
Not
an impact.
necessarily.
Why do you mean by not necessarily?
Not much, sir. Very significant, because the algorithm takes much less.
So if you look at this carefully, okay, now 10 to the power 10 divided by 10 to the power 7 degree, this is 10 to the power 3. The Alice's processor which is 1,000 times faster than that of Bob every second. Right, Nakina? So Alice or Bob which is 1,000 times faster than Bob. Well, they're not equal, right, Nakina? So both of them would impact, right? Okay. Quality of the code definitely impacts. Okay. So is the processor speed, right, Nakina? Yes, Nakina. Clear?
Yes, sir.
Okay. So now our question is, which of them runs fast? Now, if I had given both of them the same processor, then we can see a clear winner. Who is the clear winner? Bob is the clear winner, right, Nakina? Yes?
Yes, sir.
But now we have given Bob a slow processor. We have given Alice a fast processor. So we would like to see which one would run faster. Okay? Did you understand the question? Nakina? Yeah?
Yes, sir.
Okay.
Yes, sir.
Now, here's the solution of that. Okay, but let me elaborate this one so you understand this a little better. Okay. So if we come over here. Okay, so I want you to see this idea over here. This is what I have been discussing. So what is the task that we have? What is the task? The task is to sort an array containing some 10 million numbers, right, Nakina? So sort an array containing 10 to the power 7 numbers. So the input size is 10 to the power 7. Correct, Nakina? Yes?
Yes, sir.
And here's what we have, here's what we know so far. So Alice, okay, comes up with an algorithm that requires some 2n square instructions to solve the problem. Bob, on the other hand, comes up with an algorithm that takes some 50n log n instructions to solve the problem. Same problem, right, Nakina? Okay. Looking at the number of instructions required, we can see that clearly Bob requires less number of instructions. You can actually plug n as 10 to the power 7, and you'll see that this one will be much smaller than this one, right, Nakina? Yeah. So from there we know that Bob has written a better code, right, Nakina? Yes.
Yes, sir.
But if you look at the execution speed or processor speed, you know that Alice uses a computer which executes 10 to the power 10 instructions every second. Bob's computer executes 10 to the power 7 instructions every second. So Alice has a faster processor, right, Nakina? Yes. Okay.
Yes,
Yes,
sir.
sir.
And execution time depends on both the things. It depends on the quality of the code as well as the processor speed. So, but we want to see what happens now. So let's see for Alice. Now, if you look at Alice executes her code in a processor that executes 10 to the power 10 instructions every second. So 10 to the power 10 instructions are executed in 1 second. Am I correct, Nakina? Yes?
Yes, sir.
So one instruction is executed in how many seconds? 1 over 10 to the power 10 seconds?
Yes, sir.
And Alice uses a computer that requires 2n square instruction, where n is 10 to the power 7. So 2n square, n is 10 to the power 7 whole square instructions requires some 2 times 10 to the power 7 whole square divided by 10 to the power 10 seconds, right?
Yes, sir.
And that's exactly how we can find that the exact runtime that this Alice's program would require to sort these 10 to the power 10 million numbers. Okay. Similarly, I can also find out the runtime taken by the Bob's algorithm. So how do we do that? See, Bob uses a processor that executes 10 to the power 7 instructions per second. So 10 to the power 7 instructions in 1 second. One instruction in 1 by 10 to the power 7 seconds, and 50n log n instruction is 50n log n divided by 10 to the power 7. 50n, n is 10 to the power 7. Log of n, n is 10 to the power 7 divided by 10 to the power 7. Correct, Nakina? Yes?
Yes, sir.
Now, if you compare the Bob's Bob solution would take 1163 seconds to solve the problem, whereas the Alice's solution would take some 20,000 seconds to solve the same problem. Now, let's try to put it in perspective, and you see 20,000 seconds is actually larger than 5.5 hours. That means the Alice's solution requires more than 5.5 hours to sort these 10 million numbers. Right, Nakina? Yes?
Yes, sir.
What about
Yes, sir.
Bob? Bob requires some 1163 seconds. If you convert this into minutes, you will see that actually it takes less than 20 minutes. 20 minutes to come like that, to solve the same problem. So you see, despite the fact that Bob has a slow processor, he can solve it in less than 20 minutes, which Alice requires more than 5.5 hours with a faster processor to solve. Right, Nakina? Yes?
Yes, sir.
Now, this clearly explains us that why the quality of code is so important. This clearly explains us, that Bob's code actually has taken less resources, right, Nakina? Yeah, in terms of time, you can see it takes much less resources, right, Nakina? Yes? Okay.
Yes, sir.
And so this actually stresses the fact that, why analyzing an algorithm is so important to us, because analyzing an algorithm helps us to see how well or how poorly an algorithm is working. And you can clearly say that just because someone has written a better code, you can clearly see how remarkable the result is. One is taking more than 5.5 hours. The other person with a slower processor is taking less than 20 minutes to solve the same problem. Okay, clear, Nakina? Is that okay? So I hope after this concrete example, you can actually appreciate the fact why we stress on not just any solution, we stress on an efficient solution, right, Nakina? Clear? Okay. Is this okay, Nakina?
Yes, sir.
Does
Yes, sir.
anyone have any questions so far?
No, sir.
No. Okay. If you don't have any question, then I'm going to stop the recording.